Hello once more, and welcome to our final video lecture for Physics 110C. This is video lecture 17.4, in which we're going to discuss the content from section 7 in chapter 17, of course. And that is, we are going to talk about a phenomenon called the Doppler effect, which it turns out is both common and technologically and scientifically important. Here's the key idea. It's a short description of what the Doppler effect is in words. It is the change in observed frequency of a wave. Observed means what you detect, what you hear, what you receive, what you measure, whatever word you want to use. The change in the observed frequency of a wave when the source or the detector moves relative to the medium. Right? A sound wave, because we're talking about sound waves here, has to have a source. Something has to create the sound wave. And as far as the Doppler effect is concerned, also a detector. Something has to detect, receive the sound wave. And here we're talking about the frequency of the sound wave. And there'll be a frequency emitted by the detector, by the source, and a frequency measured by the detector. And if there is relative motion between those two things, the source and the detector, then the frequency emitted by the source and the frequency received by the detector will not be the same, not necessarily. That's the phenomenon. Let me show you an example in the real world of this happening. I bet you have all heard of this example before, but I want to show you a YouTube video of it. You can find many YouTube videos like this. And it is the quaint but somehow reassuring phenomenon of a train whistle, or horn, I should say. And what the video is going to show is a train, and it's approaching us as the observers with its horn sounding. And we, in the recording of the video, are standing on the ground beside the track, are detecting the frequency of the sound wave. And initially the train is approaching us, but then it passes us and goes by. So it changes from approaching us to going away from us, if you like, from approaching to receding. And our observed frequency, our detected frequency, clearly changes as the train switches from approaching to receding. And that change in that observed frequency is very pronounced, and that's an example of the Doppler effect at work. So let me switch over to the YouTube video. So there we are, standing at the side of a railroad track somewhere out in the country. The train's going to be approaching any moment, and it's going to be sounding its horn. Here it comes. Okay. So the point was that clearly detectable change in frequency of the horn, or the sound from the horn, from a higher frequency to a drop to a lower frequency. Okay? That's an example of the Doppler effect at work. Okay? And so now what I want to do is I want to have us start to understand the physics of that phenomenon and how to quantify the change in the frequency that you detect because of this relative motion. Now, it turns out we need to consider two separate cases. So we'll do these one at a time. Okay? And the first case we're going to consider is the case where, remember, you got two things. You got to have a source of the sound wave and a detector of the sound wave. So in case one, we're going to have the detector moving, but the source of the sound be stationary. So that's what we're going to do. The thing that's producing the sound waves is at rest, and the thing that's detecting the sound waves is moving. So let's start with a schematic picture. Very schematic, but it's getting across the key physics. The dot here in the center of our picture, labeled S, is our source. And let's assume it's a spherically symmetric source, so it's emitting sound waves uniformly in all directions. And these series of ever larger circles represent consecutive wave fronts in the sound waves that are traveling outward. Note the distance between two neighboring wave fronts would be the wavelength, lambda. Okay, now the source is at rest relative to the medium in which the sound waves are traveling. This is probably going to be air, but you can also have sound waves traveling in water, for example. But in any event, whatever the medium is, the source is at rest relative to that. And it's emitting its sound waves, okay, in all directions. Now, the detector is represented in this schematic by this disembodied ear, rather grisly thing, but the ear is just meant to have you think about that being the detector, D. And in this picture, the detector is moving to the left. That V sub D stands for the velocity of the detector. The direction of that motion is important, meaning that the detector is moving towards the source in this picture. The other red arrow is labeled V. Well, that's just the velocity of the wave fronts from the sound waves propagating outward from the source. Okay, so in this scenario, the detector is moving towards the source, and the source is at rest. What frequency will the detector, frequency of sound, will the detector detect? Well, one thing we have to be clear about, let's just use the symbol F to be the frequency emitted frequency by the source. Okay? That's the frequency it emits. Let's use F prime, I'm using your book's notation, to be the frequency that the detector measures. So I'll just call that the detected frequency. That's the frequency of sound that ear will hear. Okay? F prime. My question is, how is F prime related to F? How is the frequency that the detector measures, how does that compare to the frequency emitted by the source? All right, now, here's the key thing. If the detector were at rest relative to the medium, just like the source is, then it's pretty clear that the detected frequency F prime would have to be the same as the emitted frequency F, because the detector and the source are at rest relative to each other. But what if now, as the picture shows, the detector is moving towards the source? Okay? Well, because of that motion towards the source, the detector is impinging on, intercepting more of those wave fronts per second than if the detector were just at rest. And it's the number of wave fronts intercepted per second that is the detected frequency of the wave. And so, if the detector, because of its motion towards the source, is intercepting more wave fronts per second compared to when it was at rest, then the detected frequency F prime should be higher than F, the emitted frequency. F prime should be a larger number than F. Conversely, unlike what the picture shows, if the detector were moving away from the source, then the detector would be intercepting fewer wave fronts per second compared to when the detector was at rest. And so the detected frequency F prime would be less than F. that's the main idea. That's how you get f prime to be different from f in this case. The motion of the detector results in a different number of wavefronts per second being detected, and that's what gives you the different frequency. Now I want to show you that now on a Wiley Plus animation. We'll actually do some simple calculations with simple numbers so that you can see a little bit more clearly, hopefully, what I'm talking about. All right, so now let me go to a Wiley Plus animation in which we have a coordinate system and we have a source of sound that is sitting at the origin. It's that large black dot at the origin, and that source of sound is not going to move. It's stationary. And the first thing I'm going to do is just run the animation, and it's going to start in case 1 with the detector, the receiver, also being at rest. So the source and the detector are both at rest relative to the medium, the air, and therefore they're at rest relative to each other. Okay? All right, and then we're going to figure out the period and the frequency of these received or detected sound waves in this case. So all I have to do is run the animation, and we get wavefronts emitted every period. And they intercept the receiver. The receiver is the red dot. Okay? And the period of the sound wave is the time between 2 successive wavefronts to be received. Okay? All right, so I'm going to now adjust the time slider, and I'm going to try my best to bring it back to the case where the first wavefront impinges on the receiver. See it right roughly there. Now look at the time value. You can see it's almost 5 seconds. In fact, I'll tell you it's 5 seconds. Okay? Now let me slide the time slider until the next wavefront impinges on the receiver. And let's see how much time has elapsed. Looks like it's 6 seconds, isn't it? So the time interval between 2 successive wave fronts is 1 second. That's the period of that wave. All right, so now let me go back to my notes here and let me jot some things down. I'll do it over here to the side. First, we have the case where everything was at rest. Source is at rest, receiver or detector is at rest. The period, 1 second. Now, by the way, this is just, the numbers here are chosen just so that they're nice and simple. You can't hear a sound wave with a period of 1 second because it would have a frequency of 1 second. Let me write that down, or excuse me, 1 hertz. And a human here cannot hear 1 hertz, but the numbers here are just chosen for simplicity. Okay, if you like, that's the emitted frequency, 1 hertz, directly from the source. All right, now let's go back to the animation. We'll reset the slider. And actually, before I do anything else, I'm also going to do a little kind of a game where I'm going to run the animation, and every time a wavefront impinges upon the receiver, the red dot, I'm going to make a pinging sound like that. Ping. And the rate of my pinging is the frequency. Okay? So here everything's at rest. Ping, 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 ping. The rate of that pinging is the frequency at the receiver. All right. Now I'm going to click this button that says toward source. And now when I run the animation, the source will be at rest relative to the medium, but the receiver or the detector will move towards the source. That would mean to our left. And I'll just do the pinging game first, and the rate of my pinging when a wavefront impinges on the receiver will be the new frequency received. So let's see if we can get any feeling for what that new frequency is. Note the receiver is moving. Ping, 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 ping. More rapid rate of pinging. The frequency is now higher. You see what I'm saying? All right, let's get some numbers to this. Let's try to get the first wavefront at the center of the receiver. Okay? And then we go from there to the second. And how much time has elapsed from there to there? And I'm just going to tell you how much time that is. It's 0.75 seconds. So I'm going to go back here now, and I'm going to write down, for the case receiver moving toward source, the observed period is 0.75 seconds. So the observed frequency, I really ought to write this now as f prime, is 1 over, I'll call that t prime, 1 over that period t prime, and that's 1.3 hertz. So compare then. When both were at rest, source and detector, relative to each other, the detected frequency is the same as the emitted frequency, 1 hertz. When the receiver moves towards the source, the detected frequency f prime is up higher, now at 1.3 hertz. Remember the more rapid pinging I did. Now let me go back to the animation, reset it, and now we're going to let the receiver, the detector, move away from the source. So the red dot will move to our right. And first I'll play the pinging game, and we'll just listen for the rate at which the pinging happens. That will be the detected frequency. Note the receiver is moving away from the source. Ping, 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 ping. And I didn't even get to the last wavefront. The rate of pinging is lower. The observed frequency is lower. You can try to estimate the period here by starting with the first wavefront where it's centered on the receiver, roughly about at that time, and then how much time elapses until the next wavefront is in the center of the receiver. About that. And I will just tell you that amount of time is 1.5 seconds. So, now let me write for receiver moving away from source, the observed period is 1.5 seconds. So the observed frequency, which is 1 over the observed period, is 0.67 hertz. So now the detected frequency, when receiver moves away from source, is less than the emitted frequency. 0.67 hertz is less than 1 hertz. So the point being, source is at rest, detector is moving. If detector moves towards source, that makes the detected frequency higher. If detector moves away from source, that makes the detected frequency lower, compared to the emitted frequency. And that's one way you get a Doppler effect. Stationary source, moving observer, detector, receiver, whatever word you want to use. But then there's another case. I want to talk about that next. Case 2. That's the case where the source is moving and the detector is stationary. And that turns out to be a physically different situation than case 1. All right, so now first we start with a static image, and then we'll show an animation. All right, now, there's a lot going on in this image, but here's what's happening. The source is represented by a dot labeled S. The detector is represented by the ear. The detector is at rest relative to the medium. V of the detector is 0. The source is moving relative to the medium. V sub S is not 0, and the picture shows it to the right. So the source, the thing emitting the sound waves out in all directions, itself is moving relative to the medium, the air, for example. Okay. And at some fixed rate, frequency f, that source emits wavefronts. The picture shows 7 successive wave fronts. And the location of the source, where it was when each of those wave fronts was emitted. Those are those colored sequence of dots numbered S1 through S7. So the dot labeled S1 shows you where the source was located when wavefront W1, the first wavefront, was emitted. Note in this picture, wavefront W1 is now way out on the outer edge. Versus the dot labeled S7, that's the location of the source when wavefront W7 was emitted. Notice W7 is the inner wavefront because it's the most recent one. All right, note, because that the source itself is moving to the right, our right, the wavefronts are getting bunched up on the right, but spread out on the left. And our detector is over there on the right. So when the source is approaching the detector, like the picture shows, you get the bunching up of the wavefronts. If the detector, I'll just call it D, were over here to the left of the moving source, then the source would be moving away from that detector, and that detector would be experiencing more spread out wavefronts. What is the spacing of the wavefronts affect? It affects the wavelength of the waves, because that's what the wavelength is, the distance between two neighboring wavefronts. So here's what I'm going to point out. If you look very carefully in this drawing, right there, they emphasize the distance between two neighboring wavefronts on the side where things are bunched up, and they call that lambda prime. If you want to call that the detected wavelength, notice it's smaller. Or it's small. I guess I should just say small. Versus if I were looking at that detector over on the left, where the wavefronts are spread out, then the wavelength, which would be a distance like this, is going to be larger than normal. Okay, so the lambda prime is changed by the motion of the source. And that's what I want to show you now on the animation. It's that changing of the wavelength, by the way, that's going to then also give you a change in detected frequency, because frequency and wavelength are related. F equals V over lambda. All right, so now let me go into Wiley Plus and choose a different animation. Okay? Okay, again, we have a source represented at the moment by a black dot at the origin, and two receivers, each represented by red dots. One receiver to the right of the origin happens to be at x equals 30 meters, and another receiver to the left of the origin at x equals negative 30 meters. And when I run the animation, a couple things are going to happen. The source is going to start moving to the right, and at a fixed rate, it's going to emit wavefronts. Okay, now I'm going to tell you something now that is not immediately clear from the animation. But here's what I'm going to tell you. If the source were stationary, like those receivers are, and emitted its sound waves, I'm going to tell you what the wavelength would be, because we're going to need that for the numbers I want to work with. Okay? All right, so I'll get myself back to this screen. And I will write up here for the case when everything's at rest, the wavelength of the emitted sound waves will be, I will write that down here so you can see it, 3.75 meters. Okay? That's the wavelength the sound waves would have if the source were stationary. All right, now I want to go back to the animation. And like I say, I'm going to run it. Again, the source is going to move to the right and emit wavefronts at a fixed rate. And let's just start by looking at what the picture looks like. Here we go. Okay. All right. So the source is moving to the right. It emitted wavefronts at a fixed rate. And because it's moving to the right, on the right side, the wavefronts are bunched up close together, and on the left side, the wavefronts are spread out. And the distance between two neighboring wavefronts is the wavelength. So I want us to look for receiver 1 and receiver 2 and estimate what the detected wavelength will be. Notice we're focusing on wavelength in this case. So look at receiver number 1. Receiver number 1. There's a wavefront passing right through it at x equals 30 meters. And how far to the next wavefront? You got to look carefully. The distance from the wavefront at receiver 1 to the next one beside it is 2.5 meters. 2.5 meters. That's the wavelength for receiver 1. So, let me go back here so I have my screen. And we'll put here for receiver number 1. That's the one where the source is approaching the receiver. What's the detected wavelength, lambda prime? It was 2.5 meters. So, here's what I'm going to do. Let me take the ratio of lambda prime to lambda. The detected wavelength for receiver number 1 over the emitted wavelength. 2.5 meters over 3.75 meters. This is a unitless ratio, and it turns out that that ratio is actually exactly 2 to 3, 2/3. Okay, now that's the ratio of the detected wavelength to the emitted wavelength. But remember, wavelength and frequency are inverses. F equals V over lambda. F is upstairs, lambda is downstairs. So that means the ratio of the wavelengths, lambda prime over lambda, is 2/3. Then the ratio of the frequencies, F prime over F. The detected frequency over the emitted frequency is 3/2. Invert 2/3. So F prime is 3/2 times F. Point being, F prime is larger than F. The observed detected frequency is higher. Source moves towards receiver, detected frequency is higher. Okay? All right, now let's go back to the animation. And let's look at receiver 2 and estimate the detected wavelength. Got to look carefully. There's a wavefront passing right through detector 2 at negative 30 meters. And then what's the distance between that wavefront and a neighboring one? Look carefully, just the distance, it's 5 meters. So that's the detected wavelength for receiver 2, 5 meters. So let me now write that on my notepad. We'll do that over here. For receiver number 2, and for that receiver, we could say the source is receding, going away. The detected wavelength, lambda prime, is 5 meters. So let's get the ratio of the detected wavelength to the emitted wavelength. 5 meters over 3.75 meters. And 5 over 3.75 is exactly 4 over 3, 4/3. But frequency and wavelength are inversely related. So the ratio of the detected frequency to the emitted frequency is 3/4. Or to say it another way, F prime is 3/4 times F. And now the detected frequency is less than the emitted frequency. So when the source moves away from the detector, the observed frequency goes down. We can take both those cases. and kind of combine them to get one upshot. Okay? Whether you're talking about a moving source or a moving detector. For those two things, motion towards makes the frequency go up, motion away makes the frequency go down. That's the gist of it. Okay? In fact, what you could do in this case is you could imagine a scenario like this. So let's not even worry about this detector over here right now. Just think about the detector we've got here, right there. And the picture shows the source moving towards that detector. And we know in that case the detected frequency is higher. F prime is 3/2 of f. But eventually the source will pass the ear, the detector, and then go away. So it will transition the source from approaching to receding. Once we're in the receding situation, the detected frequency is that value. So if I imagine the source coming towards me, passing me and going by, my detected frequency will change from 3/2 f to 3/4 f. It will go from higher, 3/2 f, to lower, 3/4 f. It turns out that for those numbers, that's a drop of 50%. A 50% decrease in frequency. That would be noticeable. And that's exactly what you were observing in that YouTube video. The train horn, the source, was approaching, and then it transitioned to receding. And when it made that transition, the frequency went from higher to lower, and you could hear that drop in the frequency. Okay, so the YouTube video was giving you an example of this case too. All right, now, we want to be able to handle those two cases combined, because you could certainly have a situation where the source is moving relative to the medium and the detector is moving relative to the medium. And then the big question was always going to be, what frequency is the detector going to detect? All right, now, we need to be able to just derive the formula for calculating that detected frequency. I'm not going to go through all that math and physics, but it's some good stuff, and if you want to see it, read section 7 in chapter 17. I'm just going to tell you what the result is and give you some warnings and suggestions and tips for how to use it properly. It's a very powerful tool, but like any powerful tool, it's kind of complicated and has to be handled with care. So here we go. I'm just going to now tell you the big answer for the expression for calculating the detected frequency f prime of a sound wave. It is this formula right here. And it requires unpacking. So here we go. All right, I've already said what that symbol is. F prime is generally speaking, what we're interested in. The detected frequency by the receiver of the sound wave. All right, what's this F here? F is merely the frequency measured when at rest relative to the source. If you like, it's the emitted frequency. It's what you would detect if you were sitting right beside the source. Just sitting with the source. All right? Then we've got a bunch of V's in this formula. 3 different kinds of V's. There's a V sub D, and a V sub S. Okay? Here's the first thing I want to point out. All V symbols, well, I'll just write them like so. Whether it's a V sub S, or a V sub D, are speeds, not velocities. Sorry about that, but that's the way this formula works. They're speeds, not velocities, so those V's can never be negative. No negative values for any of them. And you'll see I've got them all listed below as speeds in bold and italic. All right, the first V is just V itself. It sits there and there. What does that symbol stand for? Right there. The speed of the sound in the medium. And for us, that's either going to be air, or, as I do in class with an example problem, water. Sound waves travel in water. Okay, so that's what the first V is. Then in the numerator, there's the symbol V sub D. What does that stand for? V sub D is the speed of the detector relative to the medium. Oh boy, watch out for that. It's got to be measured relative to the medium in which the wave is traveling, not necessarily the ground, unless the medium is at rest relative to the ground. So imagine a sound wave in air. You could have a day when the air is calm. The air is not moving relative to the ground. Then the speed of the detector relative to the air is the same as the speed of the detector relative to the ground. But you could also have a day where there's wind. That means the air is moving relative to the ground. Then the speed of the detector relative to the air and the speed of the detector relative to the ground are not the same. But it turns out in the derivation of this frequency formula that the Vd has to be the speed of the detector relative to the medium in which the wave is traveling, like air. So what that really means is that there's a chance you'll have to do one of those relative velocity calculations. And I'm going to do that in an example problem in class. Now there's one other V symbol in this formula. It's in the denominator, V sub S. What does that stand for? It's the speed of the source, but again, relative to the medium. Source. So notice, the speed of the detector is in the numerator of that complicated formula. The speed of the source is in the denominator. Both of those speeds, V sub D and V sub S, are measured relative to the medium in which the wave is traveling. And then one other thing you have to unpack in this formula is we've got this plus or minus sign in both the numerator and the denominator. Well, that's because the formula is they're wanting it to be general and handle all possibilities. But when it comes down to actually using this formula in a problem, we're going to have to figure out for both the numerator and the denominator whether it's a plus sign we use or a minus sign. And the determination for the numerator and the denominator as to which sign you use is done individually. You got to deal with the numerator and the denominator, and they are completely independent of each other. And I want to spend the rest of this slide talking about how we figure out what's the correct sign. I'm going to get rid of all that junk so we can see that equation clearly. Okay, so all the words now in red that I'm going to talk about next are all about determining whether you use the plus sign or the minus sign in the numerator, and then the plus sign or the minus sign in the denominator. That's what this is all about. Signs. First, the numerator. Okay? The sign in the numerator is all about what the detector is doing. Okay? And here's what it says, looking there at the first red bullet. If the detector is moving toward the source, regardless of the motion of the source, remember, motion towards wants the frequency to go up, so choose the sign in the numerator that makes the frequency bigger. Well, that would be the plus sign. Conversely, if the detector is moving away from the source, regardless of the motion of the source, motion away wants the frequency to go down less, so pick the sign in the numerator to make the frequency less, so pick the minus sign. Let me draw some pictures of that, okay, of what that's saying. I'll use a dot to represent the source and another dot to represent the detector. And in case 1, right here, the detector is moving toward the source, so I'll put an arrow there. And I don't care what the source is doing, so I'll put a double-headed arrow there. I don't care which way the source is going. All I care about in case 1 here is that the detector is moving towards the source. That wants the frequency to go up. So in the frequency formula, in the numerator specifically, I choose the plus sign to make the numerator big. And I don't care what's happening in the denominator, so I'll just put an empty box. This picture is only telling me what to put in that numerator. Now case 2, I'll come over here and draw the source and detector again. And I don't care what the source is doing, but the detector is moving away from the source. Motion away makes the frequency go down. So I pick the sign in the numerator to make the frequency smaller. So I pick the minus sign. And I don't care what is going on in the denominator. And that's what I do for cases 1 and 2. And that's how you figure out what sign to put in the numerator. It's all about what the detector is doing. Is it moving towards the source or away? That's simple. Okay, now we talk about the motion of the source, which is going to determine what sign we use in the denominator. Case 3, I'll call it. If the source is moving towards the detector, regardless of the motion of the detector, okay, motion towards wants the frequency to go up. So let me draw a picture. We'll call this case 3. Let me revise my picture here for case 3. Source is moving towards detector, and I don't care what the detector is doing. So I'll draw it like that. That's case 3. Motion towards wants the frequency to go up. But the source's motion determines the sign in the denominator. Vs is in the denominator. So I have to pick the sign in the denominator so as to make the frequency bigger. Well, in a fraction, to get an overall bigger output, you make the denominator smaller. So to make the denominator smaller, I pick a minus sign. See what I'm saying? It's all based on the idea that motion towards wants the frequency to go up, but I'm working with the denominator. So I pick the minus sign to make the denominator smaller. All right, and then what I'll call case 4. So in case 3, you use a minus sign in the denominator. Now case 4. The source is moving away from the detector, regardless of the motion of the detector. Okay, motion away wants the frequency to go down. So let's draw a new picture over here. Note, by the way, over here in case 3, I don't care what the numerator is. Case 3 is all about the denominator. All right, now we're doing case 4. And in case 4, the source is moving away from the detector. And I don't care what the detector is doing. Okay, motion away wants the frequency to go down, to be less. Talking about the motion of the source. So I'm talking about the denominator. To make that number smaller, I want the denominator to be as big as I can get. So I choose a plus sign. And I don't care, I'm not worrying about the numerator. That's case 4. You use a plus in the denominator. So when I do my Wiley Plus example problem in class, you will see that I will do the same kind of reasoning. I will draw a picture showing what the detector is doing and figure out from that what sign to put in the numerator. And then I will draw a picture showing what the source is doing and use that to figure out what sign to put in the denominator. And then I just need to make sure that the VD and the VS values are all speeds measured relative to the medium, and then I should be able to use this formula correctly. But it does take practice. So we will do an example problem in class, and if you do the bonus practice for Chapter 17 on Wiley Plus, you'll get to practice with some Doppler effect problems. But I can't end the semester in terms of video lectures without giving you one more class engagement exercise. since practice with the Doppler effect is very important. So, one more, at least as far as Physics 110 is concerned. We'll have more, of course, in Physics 111. One more class engagement exercise on Blackboard for Physics 110, practice with the Doppler effect. Here's a scenario. The figure indicates the directions of motion of a sound source and a detector for 6 situations in stationary air. Okay, we don't have to worry about moving air. That's good. For each situation, the question is the detected frequency more than or less than the emitted frequency? In other words, is f prime greater than f? Or is f prime less than f? Or is there not enough information to tell? Okay, that's what you have to answer for these 6 cases, A through F. F prime is greater than F prime is less than F, or not enough information to tell. Now let's just be clear what's happening in the 6 cases. In each case, we're telling you something about motion of source and detector. In case A, source is moving towards detector, detector is at rest. Case B, source is moving away from detector, detector is at rest. Case C, source moving towards detector, detector moving away from source. Case D, source moving away from detector, detector moving toward source. Case E, source moving toward detector, detector moving toward source. And finally, case F, source moving away from detector, detector moving away from source. In each of those 6 cases, you state either f prime is bigger than f prime is less than f, or not enough information to say. And that's what you will enter on Blackboard. Okay, like I say, we'll do an example problem, a Wiley Plus problem of the Doppler effect in class. And that's all for this last video.